Okay, so let's start. Good evening, everyone. I am Harshit Agrawal. Welcome to the 10th live session of mine for week 10 of the course Structural Dynamics CE07. So, in today's session, we will cover following things. First, we will just review what was covered in the last session, that is in week 9 of this course. Then, we will see what was taught in week 10, a brief overview just to brush up the content and get everyone on the same level. Followed by recap and overview, there will be series of three questions, each one different from the other, based on the content covered in week 10 and assignment 10. I will first explain you the question and then step by step we will solve the question. So make sure you all have a pen and a paper besides you so that you can solve along with me. So just like the past sessions of mine, I will step by step guide you how to code in MATLAB and we will see the results. So if you have access to MATLAB, just keep it open in your laptop or PC. Else, just write syntax along with me and try to replicate it later on. And if any doubts, can ask me in the next live session. So I hope everyone are clear with the instructions. If you have any doubts, can raise your hands or write your query in the chat box. I will respond as soon as I will see. So let's start. So in the last live session that was for week 9 of the course structural dynamics, we talked about 3D dynamic analysis, which enables us to analyze a structure in near real field conditions by considering both transitional and rotational degree of freedoms. Apart from this, we learned about generation of elastic design response spectrum, which is useful for application of structural dynamics knowledge to earthquake engineering, especially while designing new structure or for seismic safety regulations for existing structures. Now, how 3D analysis is seen. So, in this, there is both transitional as well as rotational degree of freedom. So, fixing one degree of freedom to unity and others to zero, we learned how to develop mass and stiffness matrix. In planar view, we get an idea of which columns or series of column contribute to opposing motion along one degree of freedom. So, like in x direction, if the force is applied in x direction, so you can see in the figure kd and kb will show opposition because they are in plane. They are parallel to the force, while out of plane columns that are kc and kb won't show any opposition. And to oppose rotation, moment is considered with respect to center of mass. So based on these concepts, we formed a mass and a stiffness matrix. Now there are two cases: symmetric and unsymmetric system. So in symmetric system, both center of mass and center of stiffness lie at the same point. Now, how to find these points, we will see today once through a numerical. Now, since center of mass and center of stiffness are at the same point, there is no eccentricity. Hence, there is no torsion. Now, what this does, it simplifies our mass and stiffness matrices into an already decoupled matrice, as you can see in the matrices on the screen. So mass matrix is simply a diagonal matrix and the stiffness matrix is also a diagonal matrix. So it is a decoupled system. So in 3D system, so a 3D system gets converted into a n number of single degree of freedom systems whose solution techniques we are well aware of from the initial content of this course. However, when center of mass and center of stiffness don't lie at the same point, the system is said to be unsymmetric, and hence it has some eccentricity which brings torsion into action. In simple words, such system, if are subjected to say x direction translation due to unsymmetry in mass or stiffness, we not only the system not only translate along x direction but it will also rotate. Now in these stiffness in these system, stiffness matrix is not decoupled. Thus, it needs to be decoupled first and then solved. Again, the methods for which we are well aware of from the week 6 to week 8 content of the course. So you can see the mass matrix is decoupled, but the stiffness matrix is not a diagonal matrix. It is not a decoupled matrix. Now, last week, that is in week 10, we learned about vibration of continuous systems. That are those systems where mass is distributed continuously throughout the length of the system, and thus lumping of mass can't be done. Apart from this, we learned about seismometers. That is how theory of structural dynamics is used in making a device which can record seismic response activities. The content covered in week 10 was divided into different modules as follows. In week 10, module 1, we read about basics of vibration in continuous systems, wherein we discussed about governing equation for vibration in a shear beam and its solution in space and time. In week 10, module 2, we saw an example problem for continuous system, wherein we first derived dynamic equilibrium equation for continuous system and then saw one numerical. And in the last module of week 10, that is module 3, we learned about seismometer and seismograph, the basics behind them and how they actually record responses. So, moving ahead, we'll just brush up all the formulae and relations we saw this week, so that everyone can understand numerical and MATLAB part coming ahead properly. So, just to brush up things, the dynamic equilibrium equation is given as inertia force plus damping force plus stiffness force is equal to externally applied force. Assuming that the frame is rigid and deflection can happen only in horizontal direction and mass of the supporting column is negligible, the actual frame structure can be transformed into an analytical model as shown in the figure. So this is something we have been reading since week 1 of this course. And for this, we saw different cases of undamped and damped systems under free and forced vibration, how to solve them theoretically and through numerical methods. From week 6 till week 6, all our discussion were for single degree of freedom system. But in reality, a structure is a complex system which can be seen more accurately as a multi degree of freedom system since it generally rises up to multiple floors. Thus, can't be concentrated at a single point. Thus, an actual complex structure is broken down into a multi-degree of freedom system in which number of floors is equal to number of degree of freedom, and thus this structure with concentrated mass of each floor and known stiffness of columns, assuming no lateral deformation or buckling, can be simplified into a spring block system as shown in the figure in the right. Now, in these single degree of freedom system and multi degree of freedom system, there were lump masses. That is, masses were concentrated on a fixed location, and thus variation in responses were only with respect to time and not with respect to space. But now, in continuous system, both mass, both time and space becomes variable. Thus, response is a function of both time and space. So, for a continuous beam under shear action, we derive the response as a function of time and space as can be seen on the screen. So, if u x comma t is a function of both space and time, then the function of time will be derived as a cos omega t plus b sine omega t, while with the function of x, it will be derived as d lambda sine 2n minus 1 pi x upon 2l, where lambda is nothing but omega square upon g by rho. Now, when we talk about vibration in shear beam, the structure of dynamic equilibrium equation is the same as that for single degree of freedom system and multi degree of freedom system, just the parameters changes. That is, here we have generalized coefficient of mass, damping and stiffness. Now what we mean by generalized coefficient, These are coefficients which converts a continuous system into a single degree of freedom system and thus simplifies dynamic equilibrium equation. And how we obtain these generalized parameters? Using integration of parameters, that is, that can be mass, damping coefficient, stiffness coefficient, or force with deflection profile over the length of the system. And how we get the deflection profile? That is through basic mechanics, deflection in a beam having known values of resisting force and externally loading force. So once we know generalized parameter, a continuous system is nothing but a single degree of freedom system, and we know how to solve a dynamic equilibrium equation for such systems ahead. Apart from this, we learned about seismometers. So a seismometer is a device that uses the theory of structural dynamics into practical applications for recording responses of earthquake vibration. These are based on basic concepts of undamped forced vibration in single degree of freedom system. And through a complex solution to the system, we saw how a seismograph can act as a different response recording device. That is, when the forcing frequency is smaller than the natural frequency of the instrument, the seismographs work as an acceleration response recording device, also known as accelerometer. On the other hand, when the forcing frequency is larger than the natural frequency of the instrument, the seismograph act as a displacement meter. And when there is resonating condition, that is the forcing frequency is matching the natural frequency, it act as a velocity meter. Okay, so I hope the weak content is clear to everyone. So we will proceed ahead with the questions now. So first, we will see couple of questions related to center of mass and center of stiffness calculation, as it seems to have some confusion in how calculation is done. And then thereafter, we will see one numerical problem based on this week's content. So this is the first question for center of mass and center of stiffness calculation. So the question says locate the center of mass and center of stiffness for building plane as shown below. So this is a planar view, top view of the building. We can see the stiffness resisting columns at different locations and the dimensions of the building. So I will give you a couple of minutes to think how we'll proceed ahead with this question, and then I will tell you the solution. Okay, so let's see the solution now. So, what was given in the question? We know the planar view of the building, we know the dimensions, the edges, and the locations of the stiffness resisting columns. We know the stiffness value of each column, and we need to locate the center of mass and center of stiffness. So, step one will be to set up the origin. So, let's say the left bottom corner is our origin. So, I have marked 0, comma 0 at the left bottom corner. Now, first step is to calculate the center of mass. So if the mass is assumed to be uniformly distributed, the center of mass with respect to origin will be at the center of the planar view. So it will be 30 by 2, comma 10 by 2. So it is nothing but 15, comma 5. However, if the mass, in this question, the mass is uniformly distributed. However, if the mass is not uniformly distributed, the center of mass will be calculated using following relation. So the x center of mass will be nothing but integration of x dm upon integration of dm along x length, and y center of mass will be nothing but integration of y dm upon integration of dm along y length. Okay, so in the present question, the center of mass is at 15, comma 5. Now, for center of stiffness calculation, let's assume that the external force is acting in y direction first. So, we know the columns which are parallel to the force will only resist, and the columns which are out of plane or perpendicular to the force will not show any resistance. So when the force is acting in y direction, the two columns 0.5k, the one with 0.5k stiffness and the one with 0.75k stiffness, will act as a resisting columns, and the columns one with stiffness 1k, 1.5k and 1.2k won't show any resistance. Okay, now we know F is equal to K delta, basic equation. So at equilibrium, there should be no net force and no net moments. So first we'll see no net force. The next, so if the net force is needed to be zero, the net external force will be equal to the net resisting force. Thus, F will be equal to K1 delta 1 plus K2 K1 delta plus K2 delta. Delta is nothing but the deflection in y direction. So K1 is 0.5k and K2 is 0.75k. So F will come out to be zero point 0.5 plus 0.75 k delta. So it is 1.25 k delta. This is one relation. Now, net moment is also zero. So, assuming the moment along about origin, so the and let's say the center of stiffness is lying at a distance xs from the origin. So, F into xs is equal to the moment generated due to resisting column. So, it is nothing but k1 delta into its distance from origin and k2 delta into its distance from origin. So k1 is 0.5k and k2 is 0.75k. The 0.5k stiffness column is at a distance of 10 meter in x direction from origin, and 0.75k stiffness column is at a distance of 25 meter from origin. So the moment equation will become F into xs is equal to 0.5k delta into 10 plus 0.75k delta into 25. Now we know F is nothing but 1.25k delta. So substituting F in terms of k delta and solving the relation, we will get xs is equal to 19 meter. So the location of center of stiffness from origin along x direction is 19 meter. Now, similarly, let's assume external force in x direction. So, we know the columns which are parallel to the force will resist, and the columns which are out of plane will won't show any resistance. So, in this case, the columns will stiffness 1k, 1.5k, and 1.2k will act as stiffness resisting column, and the columns with stiffness 0.5k and 0.75k won't show any stiffness. Now again at equilibrium, net force and net moment should be zero. So first, next net external force will be equal to net resisting force. Thus, F is equal to K1 delta plus K2 delta plus K3 delta. Delta here is nothing but deflection along x direction, which will be same for the whole system. Now K1 is 1.5k, K2 is 1.2k, and K3 is 1k. So F will become 3.75k delta, and net moment is will be 0. So let's assume that the force is acting, the center of stiffness is at a height ys from the origin. So force will act at that point only. So the moment generated due to force will be F into ys, and the moment generated due to columns with stiffness 1.5k and 1.2k will be, the 1.5k and 1.2k stiffness columns are at a distance 10 meter from the origin, and 1k column is at a distance 0 meter from origin with respect to y direction. So net moment equation will be given as F into ys is equal to 1.5k delta into 10 plus 1.2k delta into 10 plus 1k delta into 0. Now, substituting the value of f from the previous relation, f is equal to 3.7k delta, and solving the equation, ys will come out to be 7.29 meter. So, we have the coordinates of both center of mass and center of stiffness. So, center of mass is at a point 15, 5, and center of stiffness is at a point 19, 7.29. So, in this question, what is there? It is an unsymmetric system. So, it is a, like if the force is acting along a particular direction, we will see there will be a rotation also associated with this because of torsion. So eccentricity also we can calculate, since we know both center of mass and center of stiffness. So eccentricity along x direction is nothing but the distance between center of mass and center of stiffness along x direction. So it will be 19 minus 15, that is equal to 4 meter, and eccentricity along y direction will be 7.29 minus 5, that is 2.29 meter. So this is how we calculate the center of mass and center of stiffness, and we saw how we derived the equations for center of stiffness. Now, in this question, the center of mass was located at the center only, at the center of the planar view. So, we will see one more question just to clear the concepts of center of mass and center of stiffness, and this time with a different type of solution. So, the question is locate the center of mass and center of stiffness for building plane as shown below. So, you can see three square frames are given, and each frame, the dimensions of each frame is given, and the location of the columns are given, and each column has a stiffness of 200 newton per millimeter. And for this we need to locate center of mass and center of stiffness. The dimension of the frame is given to us. So I will wait for a couple of minutes and then we'll see the solution. Okay, so let's see the solution now. So we have been given a frame structure. The columns, the position of the columns we know, and the stiffness of column we know, and there are three square slabs whose dimensions we know, and the grade of concrete used for making it we know. So we need to locate the center of mass and center of stiffness for this building plane. Now, as the masses this time is not uniformly distributed, the center of mass will be calculated using the following relations. XCM is nothing but integration of XDM upon integration of DM along the X length, and Y center of mass is nothing but integration of YDM upon integration of DM along Y length, and the center of stiffness can be calculated by the following relation. So x center of stiffness is nothing but summation of ki xi upon summation of ki, and y center of stiffness is nothing but summation of ki yi upon summation of ki. Now how we get the solution? Again using the same relationships that we saw earlier, like in the previous question we derived this relation only. So the above, the numerator is nothing but moments, the summation of moment, and the denominator is nothing but the summation of stiffness that we got from uh, equating the net force. So if you can see in the previous solution we did the same thing. So here in the second part, the RHS is nothing but summation of moment, and LHS is nothing but summation of stiffness forces, because F is equal to K1 plus K2 plus K3 into delta, and delta will cancel out always. So it will end up like this relationship only. So we can now directly use this relationship rather than every time writing both equilibrium equations. So just to simplify the calculation, we will directly write the solution in a tabular form. Now, how we obtain the value of masses? Mass is nothing but density into volume. So, density of concrete is 25 kilonewton per meter cube, and volume is nothing but length into breadth into height. So, we know length, breadth, and height for each slab. So multiplying them, we will get masses of 62500 kg, the mass one, which is located at, and the center of mass for first slab it is at the center of that slab, because it is uniform. It has a uniformly distributed mass in that slab. So the location for first for mass and center of mass will be 2.5 comma 7.5. Similarly, mass 2 will get mass of 166,000 kg, and the center of mass for it will be at 7.5 comma 7.5, and mass 3 will be equal to 60,000 kg, and the center of mass for it will be at 7.5 comma 2.5. Now how we can calculate the center of mass for the entire system? It is nothing but m1 x1 plus m2 x2 plus m3 x3 upon summation of m, and m1 y1 plus m2 y2 plus m3 y3 upon summation of y. So that calculation we can do now easily because we know the values. And for stiffness, there are 8 columns, 3 2 3 3. Okay, now stiffness of all the columns in our case is equal this time. Just the location is what we need to find. So we know the edges, it is 10 centimeter, 10 meter cross 10 meter. So stiffness column 1, that is at the top left, will be located, the center of mass for column 1 is at 10 comma 0. The center of stiffness of column 1 is at 10 comma 0. Then for column 2 it is 10 comma 5, then 10 comma 10. Similarly column 4 it is at 5 comma 0, then 5 comma 5, then 10 comma 5, and then seventh column is at 5 comma 0, 0 comma 5, and 0 comma 10. So I'll just update this entry. The x coordinate is 0 and the y coordinate is 5, and here again the x coordinate is 0 and the y coordinate is 10. No, it was correct. 5 comma 0 and 10 comma 0. For this it is 10 comma 5, 5 comma 5, and 0 comma 5. The column 4 is at 0 comma 5. So this is column 4 and it is at 0 comma 5, 10 comma 10. This will be 5 comma 10 and 0 comma 10. Okay. So these are the positions of each stiffness columns along x direction and y direction. So the center of stiffness can we can calculate now easily, k1 x1 summation of ki xi upon summation of ki and summation of ki yi upon summation of yi. So using these relationship we can easily get center of mass and center of stiffness, and if the both point lie at the same, and if both center of mass and center of stiffness are lying at the same point, then it is symmetric system, else it will be an unsymmetric system where torsion will also come into account and we can calculate eccentricity for that. Okay, so I will leave this question here only because now the solution is very simple. Okay, so this is how we end the question 2. Now we will see third question, which is based on the content covered in this week. So let's see what question says. A beam fixed support with the fixed support at both ends and having continuous mass distribution is subjected to vibration load of zero point 0.5 kg per meter square at a forcing frequency of 5 hertz. The span of the beam is 2 meter, assuming damping to be zero. Other properties of beam include density equal to 2400 kg per meter cube, area is 0.2 meter square, moment of inertia is 5 into 10 to the power minus 6 meter to the power 4, modulus of elasticity is 3.5 into 10 to the power 6 kilonewton per meter square, and we need to determine generalized coefficients of the system, the response of system with respect to time, and comment whether system is safe for use or not. So I will wait for a couple of minutes for you to think how we can solve the question and then we'll move ahead. Okay, so let's see the solution now. So we have been given a continuously mass distributed beam fixed at both the ends. The span of the beam is 2 meter. A vibrating load of 0.5 kg per meter cube is acting, which is vibrating at a forcing frequency of 5 hertz. We know the density, area, moment of inertia, and modulus of elasticity of the beam. We need to determine the generalized coefficient of the system, the responses of system with respect to time, and we need to comment whether the system is safe for use or not. Okay, so step one will be to determine the generalized system parameters. Now, before moving to generalized parameter, we need to know the deflection profile of the beam. So for a beam with continuous loading fixed at both the ends, the deflection profile is given by epsilon x, which is nothing but x by L minus 2 x by L cube plus x by L to the power 4. Now, how we get this deflection profile? From basics of mechanics. So, first we need to know the loading condition, then we will assume the loading to be unity. When we assume the loading to be unity, we will calculate the end forces and moment, and then we will determine the deflection profile with respect to position from one end. So this is something that everyone should know from the basics. So that part won't cover again, and I will just tell you the final profile how it will look like. Now, once we know the deflection profile, the next step will be to determine the generalized system parameters. Okay, so generalized mass will be given by m dash, is which is nothing but integration of mx into the deflection profile square dx. Now, what is the mass per unit length of our system? So we know the density and we know the volume. So mass per unit length will be nothing but density into breadth into height into length. So length is dx. For a small part of the beam, the length will be dx, and the mass can be calculated as 2400 into point 2, which is the area of that area of cross section of that dx part into dx. So the mass mx will be 2400 into point 0.2 into dx, and the deflection profile we know. So we need to integrate this function from 0 to 2, and we will get the generalized mass value. So upon integration, we will get the generalized mass at 47.238 kg. Similarly, we will calculate the generalized stiffness. So generalized stiffness is given by integration of from 0 to L EI into double diffraction of deflection profile ka square dx. E value of modulus of elasticity and moment of inertia we know, and we can easily double differentiate the deflection profile. So we'll get minus 12 by L cube whole into x minus x square by L, and we just need to integrate this profile along the span of the beam. So upon integration, we will get the generalized stiffness value as 10499.7375 Newton per meter. And in the end, the generalized force is given by P bar is equal to integration of 0 to L Px into deflection profile function into dx. So Px, what is Px now? Px is the forcing, the external force. Now it was given the external force as magnitude of 0.5 kilonewton, and it was vibrating at a frequency of 5 hertz. So if we know the frequency, it is an harmonic force. So it will be given by P naught sine omega t. Now what is the value of omega? Omega is nothing but 2 pi f. F is 5 hertz. So omega will become 10 pi. So the external force is nothing but P naught sine omega t. So it is 0.5 into 10 to the power 3 sine 10 pi t Newton, and we know the deflection profile. So upon integration of the whole function from 0 to L, we'll get the generalized force to be 200 sine 10 pi t Newton. Now we know the generalized mass, the generalized stiffness, and the generalized force. We don't need to know the generalized damping coefficient since damping is assumed to be 0 in the question. So the equation of dynamic equilibrium equation will become as 47.238 x double dot plus 10499.7375 z double dot z is equal to 200 sine 10 pi t. Now this is nothing but a undamped forced vibration condition for single degree of freedom system. Okay, under harmonic vibration. So the solution of this we know from week three or week three content of the course, and it is given by, if we want the deformation at any time t, it will be given by u naught cos omega n t plus u dot naught upon omega n minus p naught by k r upon r1 minus r square sin omega n t plus p naught by k 1 upon 1 minus r square sin omega t. So remember, the first two part is due to initially induced vibration and the last part is due to the vibration induced by forcing function. Now, the initial displacement and velocity in the present question is 0. So the first two term will become 0. So there is no vibration due to initial conditions, and it is just due to the external, the final condition. So u of t will be given by nothing but p naught by k into 1 upon r square, 1 upon 1 minus r square sine omega t. Now what is r? It is the ratio of natural frequency upon forcing frequency. So so natural frequency of system is nothing but omega n is equal to under root of k by m. The k value is the generalized stiffness and the m is the generalized mass. So substituting both generalized stiffness and generalized mass, will get omega n as 14.9 radian per second. And forcing frequency, it is given in the question, that will be 2 pi f. So it is 10 pi, which is nothing but 31.4 radian per second. And thus the frequency ratio will become omega upon omega n, which will be come out to be 2.1. Now we know the value of r, so we can determine the, so this is the this is how we'll get the deflection profile with respect to time. Now if we need to check whether it is safe for use or not, we need to get the maximum deflection with respect to space and with respect to time. So how we can get the maximum deflection with respect to time? Directly also we know the value, but through MATLAB we will see how we can simply get the value. Okay, so now I am opening my MATLAB software in the laptop. You can see how to code as of now and implement it later on. We'll go step by step and define everything properly and clearly. All the syntax that I will use today are have been used in the past sessions of mine, so you just need to pay attention. If you have any doubts, you can ask me, else you can code by your own also. So just I will open my MATLAB software. So it will be a very short code. Okay, so first are the, we need to define the given values. So what are the given values? First is the mass, the generalized mass, so it is nothing but 47.238. Then the generalized stiffness coefficient, which is nothing but 10499.7375 Newton per meter. Then we know the value, the absolute value of forcing function, it is zero point 0.5. The absolute value of generalized force, which is 200, and we know there is no damping present, so xi will be 0. Okay. Now natural frequency of system is nothing but square root of k by m, and forcing frequency, it is given as 2 pi f, so 2 into pi into 5. So you can see in the workspace in the right, all the parameters that we are defining here, the values you can see on the right. So the frequency ratio will be nothing but omega upon omega n. So it is 2.1. That is what we calculated theoretically also. Now we'll move on to the estimation part. So estimation. In estimation, step 1 will be to define the timestamp over which we want to see the deflection. So we will generate a timestamp of say 500 points between 0 to 60 seconds. Now how to code for this? Using linspace command. So t is equal to linspace. First entry will be the initial point, second entry will be the final point, and third entry will be how many points we want between initial and final point. So it is 0 comma 60 comma 500. So this will declare around 5, you can see in the workspace 500 points have been declared and stored in a matrix, in a vector. Now step 2 is to calculate the displacement response. So how we can calculate this if it is displacement response? It is nothing but P naught by K 1 upon 1 minus R square sine omega t. So let's say P naught by K into 1 upon 1 minus R square is a constant C. So C is nothing but P naught by K times 1 upon 1 minus R square. And U will become C into sine omega t. Okay, so this is how we'll get the deflection profile. Now we need to estimate the maximum response value. So how will do that? U max is nothing but max of absolute of U. So you can see it is 0.0055 or 5.5 if we print the U max value. So it is 0.0055 meter or 5.5 centimeter millimeter. We could have written that directly also, since the maximum value of sine omega t can be equal to 1. So U max will be P naught by K into 1 upon 1 minus R square. So you can see directly also. So Z max is nothing but P naught by K into 1 upon 1 minus R square. Upon substituting the value, you will get 5.5 millimeter only. So both theoretically and through code, we are getting the same value. Now this is with respect to time. What will be the maximum deformation with respect to space? Since it is uniformly loaded system, maximum deformation will be at the center, which can be calculated from the diffraction profile. As we know the diffraction profile, so at x is equal to L by 2, the maximum value of deflection will come out to be 0.375. So in total, the maximum deflection will be the product of both with respect to time and with respect to space. So it will be 0.375 into 5.5. So it will come out to be 2.0625 millimeter. Now whether this structure is safe or not, we can see from the codal provision IS 456. So IS 456 says that the maximum deflection should not be more than the maximum span upon 250. The span of the building is 2 meter, or we can say 2000 millimeter. So 2000 upon 250 will come out to be 8 millimeter. Since our deflection is less than 8 millimeter, we can say the system is safe under deflection. So this is how we will solve the question. Any doubts in the question? Um, if no doubts, then this is all for today's session. I will be there in the meet for next 1 hour. If anyone has any doubts, can ask me. Thank you.